Uh, Thanks everyone. Good afternoon. We'll be talking about our journey, how we ended up creating a distributed transaction manager in workflow orchestration. I am Gaurav, architect at Flipkart, taking care of transact systems like checkout. Kaustav, can you briefly introduce yourself?
Hi, good afternoon, everyone. Myself, Kaustav. I'm working as a lead software engineer in Flipkart Transact System along with Gaurav. Yeah. Over to you.
Thanks, Kaustav. Hope my slide is visible. So, as I said, we'll be talking about our journey, how we ended up creating the distributed transaction manager. And here I'll be taking example of checkout service, which is doing a workflow orchestration there, right? So just to give a brief introduction about this. So if you would have added any item in your cart and you are clicking a place order button, you will go through a checkout process where in the checkout it will try to orchestrate with n number of read services and n number of write services and give a unified view to the customer. So for example, it will try to collect uh, address. It will try to give you option how you'll be able to modify the basket. We'll try to collect the payment. We will try to reduce the inventory, um, and it will try to make a place order, right? So that is kind of a responsibility of checkout to orchestrate and capture a good order in order management system. And just to take a simplified view here, same example, right? Here checkout is doing the orchestration and trying to do one transactions, that is capturing the order, but in this process it is doing more than one stuff. It can be more, but just for simplicity, let's take example of it has to collect the payment, then it has to reduce the inventory and then successfully write in order management system, right? So to uh, be successfully consider that the order is successful placed, all the write has to be done, payment has to be done, update has to be done. And here all these services are small microservices with a proper functional boundary. So here you will see that processing the payment itself is a small microservice which is backed by its own database, similar with the inventory system and the order management system as well. And checkout will be also having its own state. So the other problem is here the expectation is that we want to do one write or like one transaction, right? But in reality, these are small other services where the right should go to respective services. And here, each respective service will be responsible for their own right. And in case if there is any failure in the system, it should also account that as well and try to reconcile and provide a consistent view in the end. So here in the end, the problem comes to how we'll be able to provide consistency when n number of write systems are getting participated, right? And just to summarize other set of high level requirement here, consistency is one. We want to be available as well because checkout being bread and butter of the Flipkart, right? Uh, it has to be low latent because customer touch point is there. It has to be high throughput to get as much resource utilization possible. This orchestration process, at least in this example, it demands synchronous in nature. It has to be extensible in sense that currently we have taken example of two or three microservices which is taking part in this distributed, right? It can be more, and as and when it is increasing, it should be able to accommodate easily as much as possible, right? So now when we see this, it's not that this is a problem of now. um, this distributed problem is there from beginning, and there are multiple industries solved as well. So starting with one of the solve, right? The two-phase commit comes pretty straightforward, right? Why 2PC is not able to help here. So what is 2PC? 2PC is two-phase commit protocol where it does prepare and commit in phases, right? So first the orchestrator will ask all the participating processes to prepare for the transactions, and all the participating processes will reply that they are prepared. And when the slowest process has replied with the prepare, then the orchestrator will go ahead and ask for each system to go ahead and the commit, right? In this process, it will try to make sure that all the system are consistent, right? uh, there can be a scenario where when the orchestrator is asking this system to write, it can fail, right? It will not be able to commit. So for example, in this case, inventory update, it was not able to commit itself, and that's why it says failed to orchestrator. And here the responsibility of orchestrator is to understand that and ask the other uh, respective system who has all earlier said they are prepared, ask them to revert the changes, right? So with this, 2PC is able to guarantee that the transactions will be consistent in case of happy flow. In case of failure as well, it will make sure that all the right system will be consistent after some point of time, right? Here the thing is, we see that it is too chatty in nature, and here we also see that orchestrator is the single point of failure whenever, and it is also slow, right? It has to wait for all the participating system to respond, and then it will be able to take decision. So now when we look to PC and compare with our set of requirement, it is able to guarantee the consistency, right? But it is lagging in availability. It is not low latent. The throughput will be also compromised here. It will be able to do in synchronous fashion, but extensing little bit uh, challenge in a 2PC, right? Then what other industry solve we have? The other option comes is the Saga pattern. And what is a Saga? A Saga is a sequence of local transactions that will be happening within each services. In this case, for example, uh, checkout orchestrator will be having its own local transactions, and once it is executed, it will try to signal or raise a event to other system. Say for example, it will go to payment process, and they will be also doing their own local transactions and with their own persisted database kind of a thing, right? So in the end, Saga guarantees that all operations will succeed, or the equivalent uh, transactions will get compensated. So what is compensated here? Say for example, I have a sequence of transaction like process payment, update the inventory, capture the order, right? This is a sequence in which each process will execute and raise a event. Now what will happen if a system failed? Say for example, update inventory, it failed. Now I want to do a compensating actions for this update inventory, so that the changes which was done earlier will be able to roll back and end up in the end consistent view. So say for example, update inventory failed. For this, I have an equivalent action called revert inventory, right? When this will be executed, I will call and trigger revert payment, and that's where, let's say, it will go backward and start reverting all the changes which was done, right? So with this way, Saga will be able to solve the consistency in happy path and consistency in non-happy path. Now there are different ways this Saga can be implemented, right? One possible option is to go with a choreography based Saga. In choreography based Saga, um, um, the approach is like this. So there'll be an orchestrator, and the changes will be re- relayed to a event channel. In this case, say for example, checkout event channel, and there'll be participating system. They'll be listening to all the such channels, and whichever is interested for them, they will try to do a processing for them. So for example, in this case, process payment will listen that checkout has started, so it will try and start doing the payment processing. Once payment processing is done, it will release its event to its own channel. And here, say update inventory is interested, they will listen it and they will do their own processing, and that's why it will move further in the sequence. Now, if something failed here, they will try to update the same thing here, and all the system has to know if it failed, how I have to behave that as well. So that is kind of coming as a con. For small orchestration, it is pretty simple to use choreography based Saga, but as and when the number of participants are increasing in this, it is becoming cumbersome. And then another thing is that it becomes a little bit uh, uh, different, that there is no central orchestrator which knows everything, so regression and another thing becomes challenge. So that's what we are trying to depict with this grid view, where availability, low latent throughput are getting full by this choreography based Saga. But since event channel is coming in between, we will not be able to do in a synchronous fashion. And then other challenges, like it can result in a cyclic view and there is no central coordinator. So now there is another option, another way this Saga can be implemented, that is called orchestration based Saga. Here there is a central orchestrator, we call it Saga execution coordinator. So you can say it is kind of a brain, and it is the an orchestrator which knows if one step is done, what are the next step to be executed. So in this example, this execution coordinator will be publishing in a channel, say a process payment command channel. And here process payment is little bit decoupled here. It only knows that if I get this event, I have to process it and I have to just say that I am done. And here ACC will be knowing what I have to do next. So that's how uh, it, it is executing in this orchestration based Saga, and it is able to overcome some of the limitations which was there with the choreography based Saga, at least for our use case, where we were looking for some kind of a central system to know everything, uh, right? So here extensibility is a bit better compared to choreography based Saga, but still synchronous nature is not taken care by this, right? With this, I will try to hand over to Kaustav, where he will be talking about how we ended up finding other set of low level requirement, and how we evolved to our end solution, and what are the low level details for that. With this, over to you, Kaustav.
Hope I'm audible. Yeah. So thanks, Gaurav, for setting up the context. Good afternoon, everyone. So with all the high level requirement laid on place, I'll start talking from the few of the low level requirement here. So on the consistency side, so state synchronization between two systems is very necessary. If two systems are not in a synchronized state, that obviously are going to lead into a improper utilization of resources. Say for an example, checkout is talking to an inventory system to release resources, and at that point of time that RPC call fails. And if checkout is not able to detect that failure and say terminate the session, so that inventory will not be available for other consumers to be used in the platform. And it has to ensure a eventual consistency, and for that it needs a different flavors of reconciliation. Either you do a lazy invalidation or a eager one. So when I say a lazy versus eager invalidation, what I meant, say checkout has invoked a payment system to initiate a payment, and in case of any anomaly, that payment initiation need not to be invalidated then and there. because initiation does not mean that money is getting debited from the customer's account. While this philosophy might not hold true for our inventory systems, because if you have reserved any inventory and there are some anomaly detected or failure, it's best to release the resources so that it becomes available for other consumers on the platform to be used. And the system also have to understand a retrievable versus non-retrievable failure differently and act on that. Say for example, checkout is talking to inventory system to reserve some of the items. And if the inventory system fails with a non-retrievable failure, it means the product is out of stock. So customer can be shown a respective experience. While if it's a retrievable or a intermittent failure, it's best system retries again or ask customers to retry. And as Gaurav has mostly talked about, so it's a user interacted system. So it's a synchronous communication between multiple microservices. And on the scale side, because to support crazy deals, the QPS is in the order of tens of thousands, and also 99 percentile is a less than a second latency. So with all this low level requirement, tried to highlight few of the requirements and which differ from the Saga. Say Saga does not support synchronous communication, so this is not easily possible to do a different flavors of reconciliation there. Similarly, as Saga works on the asynchronous way and puts the message into the respective queues, it's not very easy to differentiate between a retrievable versus non-retrievable failure. You can obviously do that by putting a message into different message queues, but it comes with its own cost of manageability and extensibility. Similarly, Saga being an asynchronous communication mechanism, it's good for a long running transactions. While in case of checkout, it requires an immediate sort of action. Either you do in a forward transaction or try to do in a compensating way. So it's all the requirement and the constraint with the industry solutions. Our solution is going to be a hybrid one, which is called a orchestrated based Saga in synchronous fashion with a 2PC. So I'll try to provide an example. How does it work? So checkout being an orchestrator, it talks to a component called transaction manager in the prepare phase. So transaction manager is basically the component that I'm going to talk about in details in next few slides. So it has its own API layer, a storage, and as well as cache. So after the prepare phase succeeds, checkout invokes an RPC call to external systems, light system, which has its own state management and storage. And after the RPC call is successful, the commit phase is invoked to the transaction manager. So I'll try to say how we have solved a few of the problems we are using transaction manager. So the synchronization of states. So you can solve it by two ways. Either you do a read repair, that is after making an RPC call to a write system, try to do a get and to know the state. But this is a costlier operation and obviously has an extra fan out which cannot be incurred in a user facing systems. So the way try to solve is basically doing a local state management, which is done by a two phase commit approach. First you do a prepare, followed by an RPC call, and then is a commit or rollback. And also checkout needs to talk to multiple transactional systems, and the cardinality are different. Like it could be a one-to-one relationship or it could be a one-to-many relationship. So checkout, before creating any entity, it first creates the ID and maintains the state of the ID along with the transactional system it is associated with it, and also the ID what is state currently it is in. Say first before making the RPC call, it creates an entry called pending init, and after the RPC call is successful, based on the success or failure, the next state is being marked. And along with the state change, depending on the cardinality, the IDs are also marked active or inactive accordingly. Say for example, say checkout to payment is a one-to-one relationship, and user trying a payment attempt successive, that is the second attempt. So previous attempt can be nullified by marking those IDs and inactive accordingly. And on the scale side, we'll see how we have tried to solve it. So concurrency being a very important problem to deal with, because or else it will result into a improper usage of your resources and also a very difficult state to be in where you can do a reconciliation. So say a user making a request one, and as part of the request, checkout makes a get from the transaction manager. And before the request one exits, another request comes, which is request two. That's the concurrent request here, and that also does a get call. and by that time the request 2 does a put call, and request 2 also try to do a put call, but that fails because the interaction between the transaction manager and the persistent layer is basically supported by a serializable interface. So that is called a compare and set. So by doing a compare and set, you make sure only one concurrent call are going to succeed. So another scenario of concurrency, say similarly the request one is being made and checkout does a get to the transaction manager, and post that it does a put entry there, and before the request one ends, request 2 comes, it also does a get. At that time this guy gets a entry called pending entry, that is a pending init. So if any entry has a pending, that means it's a lock. So that is called a semantic lock. So semantic lock is nothing but a lock which gives a hint to the guy that this request should be treated with a suspicion, because already an active transaction are holding a reference to it, and that will be closed by a retrievable transaction, either via a forward manner or via a compensating way. Another problem with respect to stale is how you handle the idempotency. Say user made a request one and that does a get to the transaction manager, and after that it starts a transaction, that's the prepare phase. Then RPC call is made to the external service. After that RPC call succeeds, the end transaction or commit being made to the transaction manager and response being returned to the client. Say after that another request, similar sort of request comes, and it does a get from the transaction manager and it receives an entry called init state. Init state means that entity is already created, so probably does not need to invoke the external service again and return the idempotent response back. So this slide is mostly the gist that we have talked about. I have tried to solve for the concurrency by having support for cache and the semantic locking, and handling idempotency. This will reduce the fan out to the external service calls, which is a very good for a user per systems. And also it has its a cache component which solves for a high scale get calls. With this, I'll try to show how the whole order capture sequence diagrams looks with all the components in its place. So say user invokes a command place order, at that time checkout starts the transaction manager start command, and upon receiving an act, it starts an RPC call to the payments, which is a capturing payment. And after receiving the acknowledgement from there, it does an append transaction. So append is another flavor of transaction where application can differ writes to the database while states are updated in only the cache. So this gives you a flexibility to deal with the high scale, or every time you don't need to talk to the persistence layer. So similarly, after getting this app, another RPC call of inventory is made, and similarly this flow continues, and finally a capture order is being done, and upon receiving an act, checkout knows the workflow is complete, so it invokes the end transaction command, and upon receiving an act, it returns a success to the client. So to talk about some of the goodness of the transaction manager, it's a lightweight library backed by a pluggable data store. In our case, we have used HBase, but you are free to choose any of the data store that supports cache semantic. And also have a pluggable capability of key expiration. So what I mean say that the Guava cache that I talked about, you can configure hold like what number of keys that you want to keep along with the eviction policies and TTL, which helps systems to determine a sweet spot between the application performance and the memory footprint. Similarly, this does not have a state management overhead. That's the extensibility thing, that if you integrate a new write system in the existing workflow, most of the heavy lifting being done by the transaction manager, and application has very less overhead on that. And the transaction manager provides the hook capability from the API layer. It has an initiate, append, or commit functionality available, which application can latch onto, as we have shown earlier also in the diagram, like prepare phase, it calls the initiate, and the commit, it being called in the post phase. So now, with all this, I'll try to circle back to the comparative study that we started with all the solutions. So on the transaction manager side, is in the most rightmost column, we have ticked everything, like a sort for the consistency, availability also being a HA part of it, and also it's a low latent and throughput are there. And mostly it's mostly designed for a synchronous communication, solves for the user interaction nature of the systems. And it's extensible because most of the heavy lifting are done by the transaction manager, and also there is a central orchestrator which has the end view. So some of the future roadmap that we have in mind is basically to have a inbuilt orchestration support in the transaction manager itself. There where you can have a declarative way of defining all the entities along with their relationship, like what is a one-to-one or one-to-many, and there how it should be compensated, whether it's a lazy or eager invalidation. On the scale side, we have opened this on a percentage of user traffic and have planned to open it up in near future for the complete customer base. So we have few room of improvement on the scale side. And on the anomaly detection side, being a state management, you obviously want this sort of capability to have as an out-of-the-box capability so that you can build necessary alerting monitoring out of the box from this. And so these are the some of the references that we have influenced our solution from. You guys can go through if you feel interested. With this, we'll open it up for Q&A. Thank you.
I'm going to quickly check if my microphone works. If someone can respond, yes, please. Okay, that's great. Thank you so much, Gaurav and Kaustav. That was a great talk. Folks in the audience, please go ahead and take the poll which is appearing on the right side and rate Gaurav and Kaustav's talk. All of you, I'm sure, are curious to ask more questions with these guys. So please move ahead into the networking room and you can go straight to breakout room 2 speakers table and begin your Q&A with Gaurav and Kaustav. With that, we come to an end of this particular segment in the breakout room. Thank you so much for being here, everyone. I would like to guide you all towards the auditorium now. We have a quick, I think we have 10 minutes left for a quick break. Go ahead, grab some coffee, stretch yourselves out, and we'll see you back in the main auditorium for some really interesting developer lightning talks at 3:50 sharp.